We've talked a lot in this channel about prime numbers, and deservedly so, because prime numbers are extremely important as far as number theory is concerned, and number theory, of course, is extremely important aspect of mathematics. We've talked about the definition of prime numbers, we've given examples of primes, we've talked about different classes of primes, and we have even given a sort of nice real-world application of prime numbers. But there's one question that we haven't answered as yet, and that is, how many primes are there? Are there an infinite number of primes, or are there only a finite number of primes? Now, this question was actually first answered by Euclid way back in 300 BC, where he showed that there are, in fact, an infinite number of primes. Now, we're going to be back after the pause to give a very simple proof to show that there are an infinite number of primes. But what might be an idea is that if you get yourself some pen and paper and try and think how you might prove it yourself. Our objective is to actually go ahead and prove the following theorem. And the statement of the theorem is that there are an infinite number of primes. That's our objective. That's what we really want to prove. Now, the way we're going to do it is as follows. We are going to employ a strategy which is known as proof by contradiction. That's the strategy that we are going to actually employ. And this strategy is a very sort of widely used strategy. It's not just a strategy that is applicable for this particular theorem. And it works roughly as follows. So we will start by assuming the opposite of what we are actually trying to prove. So we will assume a finite number of primes. Now, the statement of the theorem says that there are an infinite number of primes, but what we will do is we will start by assuming that there are in fact only a finite number of primes. Now, what we'll find is that this assumption here will actually lead to let's say a false or strange conclusion. Right, or a conclusion which just simply doesn't make sense. So with the assumption that we have a finite number of primes, we will get to a conclusion which is actually the false or strange. Now, what does that imply? That would imply that the assumption itself of having a finite number of primes is actually not true. So this would imply that the assumption is itself not true, and if that is the case, then the opposite of what we have assumed, the opposite in fact must be true. So this is the sort of general strategy that we're going to employ in order to prove the statement of the theorem. Let's get cracking with the proof. Now, recall that we had started with the assumption that we have a finite number of primes. So let's go ahead and write that out. So we are going to assume a finite number of primes. Right, so that's our assumption. So let's go ahead and write out the various primes. So the smallest prime number is 2. The one larger than that is 3, then we have 5, then we have 7, we have 11, and we continue on till we find the largest prime P. So let's denote P as the largest prime. Right, so now let's do the following. Let's take all these prime numbers and multiply them together. So we get 2 times 3 times 5 times 7 times 11 times all the various primes in the middle times P, which is our largest prime. So let's put a bracket around them and let's add 1. And this resulting expression that we actually get, let's denote that as n. Now we're going to ask a question, and the question is as follows. Is n a prime number? That's our question. And if you think about it, you will be able to quickly work out that the answer is no. And the reason is rather simple. P is the largest prime. We've got an expression which multiplies P with all the primes before it. Then we've added 1. So clearly n is larger than P. P is the largest prime. So n is not a prime number. So as n is not a prime number, n is a composite number. N is actually a composite number and must be divisible by primes, and must be divisible by primes. So now the the proof gets a little bit more interesting. Let's start with the smallest prime number, which is 2, and ask whether n is divisible by 2 or not. Now 2 is a factor here, so clearly this expression, which is 2, which is a factor plus 1, this expression here is not going to be divisible by 2, so n is not divisible by 2. Now we get on to the next prime, which is 3. 3 is a factor here, so you've got 3 as a factor of this expression plus 1. So clearly n is not divisible by 3 either. So let's write that down. N is actually not divisible by 3 either. Now if we move on to the next prime, which is 5, we find that 5 is a factor here as well. And so by a very similar argument, we can say that n is not divisible by 5 either. So rather than writing it out, we say that n is not divisible by 5 either. Now carrying the argument forward, we can easily show that n in fact is not divisible by 7, it will not be divisible by 11, it will not be divisible by 13. In fact, it will not be divisible by any prime number. So n will actually not be divisible by any prime number. Now let's recall our assumption again. So our assumption was basically that we only have a finite number of primes. So we only have a finite number of primes. Now, so essentially with this assumption, what we have got is two statements. One is that n is divisible by a prime, but on the other hand, we have also just shown that n is not divisible by any prime. So on our assumption, or based on our assumption, we've got both of these statements coming out, that n is divisible by a prime, but then we've also just shown that n is not divisible by any prime. So obviously the conclusion that we can make is that the assumption that we made is in fact not correct. So in fact, there exists, that's the symbol for there exists, an infinite number of primes. So what we just basically articulated here is a sort of proof by contradiction. We made a certain assumption that we only have a finite number of primes, and based on that assumption we ended up getting two statements, that n is divisible by a prime and that n is not divisible by any prime. Hence the assumption must be incorrect, so the opposite must be true. So in fact, there exists an infinite number of primes. And this rather beautiful result goes all the way back to Euclid in the year approximately 300 BC.